Hello everyone, this is 4.2, graphs of rational functions. And I'm just going to start off with an example here on how to graph, and we're going to graph based on how we saw basically the horizontal and vertical asymptotes from last section. We also even graphed last section too, so this should not be that long of a video. But the main things I want to consider before actually putting the graph together are the following. So we want vertical asymptotes, we want horizontal asymptote, we want X-intercepts, and Y-intercept. That's basically it. I guess one more thing maybe is holes, but like I said, having an emphasis on plotting holes isn't too big of a deal. In this case, there's not even holes because there's no cancellation of any factor. So I'm going to leave that out. And I think that's all we really need for right now. So let's just begin, shall we? Vertical asymptotes, you set the bottom equal to 0, so let's factor the denominator. So let me show you in red that this factors as what times what. Well, in front, it's just x squared, so that's x and x. And remember, I always put minuses just as like a default, but I can change the signs as needed. The two things that multiply to 4 and have a difference of 3 are 4 and 1. And I say difference because they multiply to negative, meaning the signs will be opposite. Okay, negative 4 plus 1, so if this is a plus, then they do combine to negative 3 in the middle. If it was the other way around, it would be positive 3, but this is what we want here. So now, setting each of these equal to 0, and notice there's no cancellation with the top, we'll get the following for our x-intercepts. X is equal to 4, and x is equal to negative 1. Setting each of the factors in the bottom equal to 0. Horizontal asymptote, well, the degree of the top is less than the degree of the bottom, so this is actually case 1, and this is y equals 0. X-intercepts, to find x-intercept, you set y equal to 0. Basically, to find x-intercepts, you set the top equal to 0. And the top 2x is 0 only when x is 0. Now notice that x wasn't there, then it would be 2 equals 0 and 2 can't be equal to 0, so there would be no x-intercepts, because that equation would have no solutions, basically. Y-intercept is just plugging in 0. And when you plug in 0, you get 0 on top, and 0 over anything is 0. Notice the bottom isn't 0, so there is a y-intercept. If the bottom was 0, when you plug in x equals 0 for the y-intercept, then there is no y-intercept because you have a 0 denominator. But in any case, here it's the point 0, 0. And I should have said that here too. X equals 0 is the x-intercept, but the point specifically is 0, 0. Because remember, it's the x value comma 0. Here it's 0, the y value for the y-intercept. But in any case, it's the same point. Right, so now let's see if we can put this all together and start graphing things. So I want to graph with an appropriate scale. And the appropriate scale, I think we need to include 4 for the x values. So let me go up to 5. And let me go to negative 5, I guess. And let me just make it a 5 by 5. There we go, so here's our 5 by 5 grid. Negative 1, negative 2, negative 3, negative 4, negative 5. Perfect. So now I'm going to first, in red, I'm going to show what my vertical asymptotes are. That's at x is equal to 4 and negative 1. Perfect. Now what? Well, now our horizontal asymptote is y equals 0. Remember, y equals 0 is just the x-axis, just like that. And now we have 6 sections around these asymptotes. So I need to figure out, going from left to right, if the curve will be above or below the horizontal asymptote for each section. And well, one thing to notice also is that we have to pass through the point 0, 0, which doesn't really tell us too much, but I guess we just have to figure out by plugging things in. Let's just do that then. So over here, if we plug in negative 2, well, it's nice that we factored it, because negative 2 on top would be negative 4 when you plug it in, over negative 2 times negative 2 minus 4 is negative 6. And then negative 2 plus 1 is negative 1. So altogether this fraction is negative 4 over positive 6, which is positive 4 over 6, which is just the 2 over 3, and negative 2 over 3. Because it's positive, negative over positive, so it's going to be down here actually, at negative 2/3. But the whole point is that it's below the asymptote, so it has to look like this. make it look like it approaches more. There we go. So it approaches the asymptote. That looks a little better. I made it look like it kind of like went down, but it actually gets closer and closer as you get towards negative infinity. What about over here? Well, we'll have to plug in 1 to see what happens, or 2 or 3, but I'm going to plug in 1. When you plug in 1, let's see, what do we get? We get 2 on top, so let me erase this work. That's fine. 2 times 1. Plug in 1 on the bottom, we get negative 3 times 1 plus 1 is 2. So notice the 2's cancel and you just get negative 1/3, which is down here. So it's going to look something like this and not past that vertical asymptote. It's going to get closer towards it. All right, what about on this side? We could plug in negative 1/2 if you wanted. And I'm just going to see if it's positive or negative, because that'll dictate if it's below or above. It's not obvious, right? So let's just plug in a negative, shall we? Negative 1/2. Negative 1/2 on top is going to be negative 1 over negative 1/2 minus 4 is going to be negative, so it's a negative number. And negative 1/2 plus 1 is going to be positive 1/2, which is a positive number. So we don't really care about the number, we just care about the sign. So the denominator is negative because negative times positive is negative. The top is negative. So we'll have negative over negative, which is positive, so that's actually above. So it's going to look something like this then. Again, approaching the vertical asymptote. Great, so now finally on this side, is it above or below? Let's see. So we're going to plug in 5 into the factored version. And you can see plugging in 5, the top will be 10, which is positive. Here we have 5 minus 4, which is positive 1. And then 5 plus 1 is positive 6. So that's 5 over 3 after reducing, but it's positive. So the whole point is the graph will look something like this. Now this example, honestly, is the most complicated it can get as far as graphing a rational function goes. There's one more thing we need to discuss, and that's something we didn't speak of in complete detail last time in 4.1, and that, of course, is slant or oblique asymptotes. Here the book calls it slant, so I'm going to go with that vocabulary, slant asymptote. All right, so to motivate the explanation of what we do with the slant asymptotes and how we handle a rational function that has a graph that has a slant asymptote, I first want to talk about more of the explanation of why vertical asymptotes have those procedures we saw from 4.1, and here it is. So remember that for vertical asymptotes, f of x will approach positive negative infinity as x approaches a number, okay? And the explanation for that is the following. As the denominator approaches 0, the entire fraction will approach infinity. And basically what this says is that as your denominator gets small, the whole fraction as one number will get large. And I didn't actually compute what these are, but you can do it yourself and you'll see that this will be a number, this will be a larger number, and this will be an even larger number. So the whole point is that as your denominator gets smaller and smaller and smaller and smaller, the whole fraction will blow up towards positive infinity. Or if it was negative, it would be negative infinity. So hence the plus or minus negative infinities. Okay, and quite the opposite happens for horizontal asymptotes. So as f of x approaches a number, well, in order for f of x to approach a number, I should say, as x goes to positive infinity, well, let's see the explanation for the horizontal asymptote. And it is this. As denominators gets large, the whole fraction will approach 0. So again, it's this idea of large versus small. So here the denominator will get large, and the whole fraction will get small. Quite the opposite of what we had here. When the denominator is small, the whole thing's large. Here, when the denominator is large, the whole thing's small. And here's some example of this. Notice the numerators stay the same. Here I show 7. But notice the denominator, unlike the above example where it gets smaller and smaller, here it gets larger and larger. And I have the inequalities actually in the wrong order. But when you make the denominator larger and larger, you actually get smaller results. So the whole point here is that this fraction is going to approach 0 as the denominator goes to infinity. Similarly here, this fraction will approach infinity, plus or minus, depending on the sign. In this case, it's positive infinity, but it could be negative if there's a sign change. As the denominator gets smaller and smaller. So there's some explanation of that there. And I kind of want to show, as far as horizontal asymptotes go, those, well, I said there were 3 cases. The third case, having no horizontal asymptote, as it turns out, that can get into a digression, and we'll talk about that when we get into slant asymptotes. because that's not a horizontal asymptote. It's slanted, not horizontal. But for horizontal specifically, there were two cases. There was case 1 and case 2. So either your horizontal asymptote was the fraction of the leading coefficients or just 0 if your degree on the top was smaller than the degree on the bottom. But here, notice, if you want your denominator to be 0, one of the factors in the bottom should be 0. So the procedure for vertical asymptote should make a lot of sense with this explanation, because to find where your vertical asymptotes take place, you just have to find out where your denominator is 0. When your denominator is 0, you'll have this situation. So I hope that explanation is okay. But here, something interesting happens. What we're going to do is we're going to try to make this happen. We're going to try to get these fractions where denominators are going to approach positive infinity as x goes to positive infinity. So really what I want to do is I want to divide everything by the largest power of x. So here, let me show you. I'm going to multiply the top by 1 over x squared and the bottom also by 1 over x squared. It's going to look like a little bit of a mess, but let me try to explain. So when you do that, distributing this, we get 2x squared over x squared. The x squareds cancel, so we just get 2. Plus 3 over x squared, okay? And then here, if we distribute this, there's also some cancellation. X squared over x squared is just 1, plus 3x over x squared cancels to 3 over x, minus 5 over x squared. Now, what are we trying to do? We're trying to let x go towards positive or negative infinity. Let's just, for ease of explanation, let's just say it goes to positive infinity. Negative infinity, actually the same argument holds, but just watch me here. So if x goes to positive infinity, in each of these fractions, what's happening? In each of these fractions, since x is going to positive infinity, like we saw here, the larger your denominator, if your numerator doesn't change, and notice here that numerators in each of these fractions are constant, they don't involve x, then the whole fraction will go to 0. So that'll go to 0, that'll go to 0, that'll go to 0. What are we left with? Just the original leading coefficient at the top divided by the original leading coefficient at the bottom, which is 1. So we have 2 over 1, which is just 2. So that explains the procedure for that case where your degrees are the same. What if the degrees are not the same? Well, if the degree on the top is smaller, we can actually answer that question. Other way around, we can't, and we'll explain that in the next screen. But here, if we divide everything top and bottom by the largest power of x, which is x squared, remember, what you do to the top, you have to do to the bottom, so they have to be the same. And we're choosing the largest power of x that's either in the top or bottom. In this case, the bottom one is the winner. Distributing this, we get 3x over x squared on top, which reduces to 3 over x, minus 5 over x squared, over x squared over x squared is 1, plus 1 over x squared. And again, as x goes towards infinity, the top two terms will go to 0. This one goes to 0, and what we have left actually is a fraction that will approach 0 over 1, which is just 0 itself. They kind of cut off there, sorry, but it's just 0 over 1 is 0. So this is why, in this case, where your degree at the top is smaller than the degree at the bottom, the horizontal asymptote is just y equals 0. Now, this limiting process that I'm explaining is kind of an idea in calculus that we'll see more in that class. But for right now, we really just need to know the procedure, but I think it'd be an okay time to explain why those procedures work, and there it is. So now we're going to see exactly what happens for slant asymptotes. All right, so now finally for a slant asymptote, here's what I have to say. So rational function f of x equals p of x over q of x, where the degree of the top is exactly 1 more than degree of the bottom. In other words, degree of p is degree of q plus 1. Then we have a slant asymptote, which I'll call SA, that is the quotient polynomial that you get when you're handling the division of p and q. So if you do the division of p divided by q and look for the quotient, usually we have to use long division, but it's possible you can use synthetic division. In this case, we'll have to use long division because our denominator isn't linear. In fact, here the denominator isn't even factorable over the real numbers. So we'll see more of that shortly. But I'm going to do this example. I'm going to find all the asymptotes. It doesn't even say horizontal, vertical, it just says asymptotes. So So I'm going to find all possible asymptotes of this function. And in doing so, I'll explain why this procedure works. So let's see. The first thing I'm going to do is I am going to realize for vertical asymptotes, there are none. And the reason why there aren't any is because if you set the denominator equal to 0, well, you'll end up getting that x is equal to plus or minus I, which is not a real number. So for that reason, you can't plot it on the xy coordinate system because x and y are real number lines, not complex number lines. In fact, complex numbers don't even have a number line. They have what's called the complex plane. That's a conversation for another day. But in any event, there are no vertical asymptotes, so something to keep in mind. Horizontal, there aren't any horizontal either, because here we have degree of the top being larger than the degree of the bottom. So all we saw from 4.1 was that there are no horizontal asymptotes. But from what we know now, there is actually a slant asymptote. And how we know that is because the degree of the top is 3, degree of the bottom is 2. So degree of the top is indeed 1 more than degree of the bottom. Great. So now according to this, what do? We find the quotient. And then in doing that, I'll explain why it works. So let's actually divide. So we're dividing x squared plus 1 into x cubed plus 2x plus 2. And let's see if we remember how to do this. Let me make this 3 a little more clear. Okay, so I'm going to look at the front terms and multiply this by whatever we need to get that. So x squared times x is going to be x cubed. So now multiply each of them by x cubed. We get, not by x cubed, sorry, by x, multiply each of them by x. We get x cubed plus x. Then change their signs to subtract. Now in this case, we got kind of lucky because they actually are like terms. Otherwise, you may need to write some placeholders, but in this case, we didn't. So here, the first two cancel. And like I said, these are like terms. 2x minus x is indeed just x. And then we bring 2 down for free, so plus 2. And now we would proceed with the same procedure again, but we're stuck. Because x squared can't multiply by anything to get x because it's a larger power. So for this reason, all we can say is that this is the quotient and x plus 2 is the remainder. Okay, now what that tells me from this explanation here is that our slant asymptote is just the line y is equal to x, and that's it. But why? Well, remember that for division, the way you can write this polynomial, fraction of polynomials rather, is the quotient x. So we can write this f of x as x plus the remainder, x plus 2, over the original denominator, x squared plus 1. And now what? Well, here's where the beauty comes in. The beauty of it is that as x goes towards infinity, this whole thing is going to get closer and closer to 0. In other words, as x goes to infinity, that part of the polynomial now, or the rational function written this way anyways, the fraction part of this function will go to 0. It's negligible. Now, why does that happen? Well, if you remember what we saw for horizontal asymptotes, this is the case where the numerator has degree less than the denominator, so it'll go to 0. It has a horizontal asymptote y equals 0. So as x goes to infinity, this goes to 0. So all we're left with is just x. And again, it seems funny because you may think, well, as x goes to infinity, x goes to infinity. But the whole point of this explanation is just to show that the fraction part doesn't matter and why we only care about the quotient part. So I'm just using this example as an explanation of why that's true. We're going to see one more example, and that'll be it for 4.2. Okay, so this last example will be 2 parts. I want to graph the following. So for the first one, notice that, well, actually for both of them, the degree of the top is indeed larger, 1 more, in fact, than the degree of the bottom. So let's see. So first we're going to start by doing what we said earlier, find vertical asymptotes, horizontal asymptotes, and then x-intercepts and y-intercepts. Perfect. And then after we gather all this information, we can try to link it together to graph. So vertical asymptotes when the bottom is 0. The bottom is 0 at x being -1. Because if you have x plus 1 equals 0, just subtract 1 and there you go. Horizontal asymptote, there is none. because the degree of the top is larger. There is a slant asymptote though, and how we get that is just by dividing. Now notice, the top can actually be factored as x minus 2 times x plus 2. That's not really of particular interest to us though, because there's no cancellation with any factors, so it doesn't really do anything, but just good to keep that in mind, that you can do that to see if there's anything there, and then if not, then abandon that idea. So now we're going to actually divide. And here we can actually use synthetic division because our denominator is linear, and the box number would be -1 if you recall how synthetic division works. The numerator has coefficients 1, 0, -4, and applying the rules of synthetic division, we get 1 multiplied by the box number is -1, add down, multiplied by the box number is +1, and then here we get a remainder, but we don't care about the remainder, we care about the quotient, and the quotient has coefficients 1 and -1. In other words, it's y is equal to x minus 1. Just like that. Perfect. I may have to erase this to make room for the graph, but for right now it's okay. X-intercepts is when the top is 0. Notice there's no cancellation, and we found out when the top is 0, it's good we factored because you could just set each factor in the top equal to 0, and it's just +2 and -2. So the x-intercepts are the points, -2, 0, and 2, 0. Perfect. Y-intercepts will set x equal to 0, so here, if you cover x's, you just get -4/1, which is -4, so 0, -4 for the y-intercept. Now finally for the graph, let me make it a 4x4 grid, just so we have room for the y-intercept at -4, of course. And first, before we begin, let's consider the asymptotes. Y equals, actually x equals -1 is the first thing we saw, that's the vertical asymptote. Now y equals x minus 1 is the slant asymptote. Here there are no horizontal. Y equals x minus 1 can be graphed by considering mx plus b. So the slope is 1 and the y-intercept is -1. So we start at -1 on the y-axis and then go up 1 over 1. So we'll get this line here for our slant asymptote. Notice also we have x-intercepts at x equals -2 and x equals +2. We also have a y-intercept at -4. And no matter how you try to plot points, or no matter what you do to try to figure out how the graph will look, it has to have this shape. It has to approach this vertical line here, pass through that, and approach this line there, on this side. On the left side, though, it has to look like this, approaching that line there and approaching this line here. So in black, that is actually the curve f of x. Okay, now finally for part 2, we'll consider f of t. Here we have t instead of x, so we'll have a t-axis instead of an x-axis. Here we had an x-axis. Well, anyways, let's see. So here, if we try to factor the top, it's a difference of squares, t minus 1, t plus 1. And the t minus 1s actually cancel completely. And remember what I said earlier about cancellation. When you have cancellation, there is a hole at that factor being equal to 0. So when t minus 1 is equal to 0, we get t is equal to positive 1. T is equal to +1. So that's our hole. Also notice what we have left over now is f of t is equal to t plus 1 after we cancel. So graphing t plus 1 is actually way easy. The only thing we have to consider now is just the hole. So let me make this, I guess, a 2 by 2. But it doesn't really matter. There we go. And now what? Oh, so to graph y equals t plus 1, remember, mx plus b. So the slope is 1. There's a 1 in front of the variable. So you go up 1 and over 1. The y-intercept is at +1. So it should look something like this. Okay? Not to intersect the previous graph. So I hope that's all right. Also, there is a hole at t is equal to 1. So if you project this to the graph, you get this open circle, and that's it. Perfect. That concludes this example, but it's kind of funny because if you looked originally, since the numerator for the top was bigger than the bottom, we thought that there would be a slant asymptote for each of them. There was for the first one, but not so much for the second one because of the cancellation. So the function just reduced to a line and there was a hole from the cancellation. So that was kind of funny. This actually concludes chapter 4 in general. We're not going to discuss 4.3 as it turns out. We will discuss a lot of chapter 5 though. So I'll see you in the next videos for chapter 5. It's going to be a lot of fun. I'll see you then. Thanks for watching.